Okay, in this problem, I'd like to calculate the electric field that arises from a particular spherically symmetric charge distribution. Now, the charge density of this distribution isn't constant. Instead, it varies in space as the square root of r, where r is the distance from the center of the distribution. So if I make a quick little sketch, it kind of looks like this. Rho of r starts at 0 and then increases as I move away from the center. Now, since this problem is spherically symmetric, I can use Gauss's law in order to solve for the electric field distribution. Given that we have spherical symmetry, I want to use a spherical Gaussian surface. I'm going to call this radius r. And if I look at the problem, it wants the electric field at 1 millimeter. If I want the electric field at one particular distance, then I want to make my Gaussian surface have that distance. Now, we've been over this a lot in lecture, how the electric field in the spherically symmetric situation points in the same direction as dA everywhere. So there's an E field at the surface, there's a dA at the surface, and the E is always aligned along dA. And so we compute the flux integral through the surface. What would normally be very complicated in an arbitrary situation becomes very easy in this case. The flux is just E times A, or E times 4 pi r squared. Again, we talked about this a lot in the lecture in the text. I'm not going to repeat the steps here. So this is the flux to the surface. So if we know the flux through it, if we can know phi E, we can solve for E because we know what r is. So how do we calculate the flux? Well, we just use Gauss's law, where phi of E is equal to the charge enclosed over epsilon naught. So really this problem becomes one of just figuring out what the charge enclosed here is. Now it's somewhat complicated because the charge varies as a function of distance. Because of that, we're going to have to integrate. What we do in problems like this, where we have a non-uniform charge density, is we break the interior of the Gaussian surface, that volume, up into little segments. Again, because we're spherically symmetric here, I'm going to break up this interior volume into little shells. The interior radius of these shells is going to be r prime, and the outer radius is going to be r prime plus dr prime. And I can calculate the little volume of charge that's enclosed by one of these shells. In order to do that, I have to multiply the volume of the shell, which is actually 4 pi r prime squared dr prime, times the charge density for that shell. 4 pi r prime squared is just the area of the shell. Dr prime is the thickness, and so 4 pi r prime squared times dr prime is just the volume. Rho of r prime is the density, is the charge density per unit volume where the shell is, and since the shell is infinitesimally thick, it's very, very thin, I can approximate rho of r prime as being constant at the shell. So this gives me the amount of charge that's in one little shell. In order to calculate the total charge that's enclosed, I just have to add up all the shells by integrating. So inside my Gaussian surface, I compute Q enclosed by doing this. This is the standard way of doing these problems when I have a non-uniform charge density with a particular spherical charge distribution. Okay, so given this, how am I going to calculate this particular problem? Well, I just write down the terms, 4 pi r prime squared dr prime. I have to pop in my expression for rho of r prime squared. In this case, if I look back up at the problem, it's just r naught times root alpha r. So go ahead and put that in. Root alpha r. And so I just have to solve this integral. Well, let me bring my rho naught, my 4 pi, my root alpha outside because they don't vary as r. And what I see is I have r prime to the 2.5 times r prime dr prime left in the integral. Okay, this is actually a pretty straightforward quantity. To evaluate, this is rho naught times 4 pi times root alpha. Integrating r prime to the 2.5 power just gives me this. And I evaluate that at 0 and r, where r is the radius of the Gaussian surface. Okay, so I can pop some numbers in for this. The rho naught was 600 nanocoulombs per cubic meter. Then it was a pi, and then a square root of 500 inverse meters. And then this is going to be multiplied times r. Now I want to work in consistent units, so I'm going to use 10 to the minus 6, 3 meters for 1 millimeter radius to the 3.5 power. Okay, so here's my expression. I can multiply all these numbers out to find the total charge enclosed by this particular spherical Gaussian surface, and I find it's 1.52 times 10 to the minus 15 coulombs. Once I know this, I can solve for the E field because I know 4 pi times r squared, in this case 1 millimeter, is equal to the charge enclosed over epsilon naught. Okay, if I put all of this together, I can solve for the E field. Oops, forgot to include that. So if I just multiply these terms together and solve, I'll find the electric field at that particular distance from this particular charge distribution is equal to 13.7 newtons per coulomb.